SKs to generate a random core with that number of parts. So it's going to be kind of a two-step process that's representing the mixture we're doing. All right, so second tool, a very cool tool, is about getting central limit theorems whenever you have generating functions with nice roots. So this is a general area that's going back a long ways, at least as far as 1967, when Harper used this tool to show that Stirling numbers are asymptotically normal. Okay, so if we have, so first notice that here, if Z is a root of GS, the only way I can get 0 is if these two things cancel out, which means their moduli must be the same. So the absolute value of this would have to equal the absolute value of that. And that can only happen if this square root thing is a pure imaginary number. So it can only happen if Z is real and less than or equal to negative a quarter. And the important part of this sentence is that all roots are real and non-positive. Okay, here's the magic. Pittman, 1997, says, since our generating function is a polynomial with all roots real and non-positive, we're going to get a bunch of nice statements. It's going to be, the coefficients are going to be normal in several senses. So the first one is that the maximum of this thing, the standard deviation of my random variable, times any one of those probabilities, pk. Oh, I didn't name it here. Minus, now this is not the cumulative normal distribution, but just the regular one. Normalized with the mean and standard deviation. That's bounded for some absolute constant c. This is what we call a local approximation with normality. So individually, the coefficients look like a bell curve. Additionally, we get a global approximation. So this is going to be about sort of the analog for cumulative distribution. It's going to be about partial sums. If we let SK be the partial sums of the PIs, then the difference between our partial sum and what the normal distribution would predict now has a specific constant for how much different that is than 1 over the standard deviation. So this is our sort of global approximation of normality. And additionally, we get a tail-bound thing. So for any epsilon, there's a delta and a constant depending on epsilon, so that when you add up the weights, which are more than epsilon away from the center, that's exponentially small. in S. x. So this is what I was mentioning before, that inside some region, we're going to approximate these SKs normally. And then outside that region, we're going to say, it doesn't matter what they do out there. Because the weights that those guys are going to get multiplied by are so tiny, you can do anything there you want. So that's the basic plan, but before I sort of sketch the proof, I just want to say that this is amazing, right? What did Pittman say? That if I have in my mind a polynomial, and all I tell you about it is that it has real non-positive roots, then you know it looks like this. That's the only thing I can be thinking of. Amazing. I was blown away when I heard about it. Okay, what time is it? Yes, I will say a few words about the rest of the proof. So, we have all our tools, we have a basic strategy. Now all we have to do is put them together and prove our theorem. So what we're interested in is this f of x, which is the probability that s is at least x standard deviations above the mean. And we're going to first break this probability down by conditioning on k. So there's a probability pk that my core has length k. And then if that happens, the correct probability to put here is this. And now I would like to replace this with a capital phi thing. But that should have mu k and sigma k here. We're going to have to do a little replacement. So in order to rewrite this in terms of the appropriate mean and standard deviation, instead of just x, we get something that depends on both k and x. We'll call it yk here. And now we can say this thing is approximately normal inside that range. And outside that range, these probabilities are multiplied by weights that are so tiny they don't matter. So this is approximately a sum of pk's times capital V's at these yks. And now the next step, which came out of some computer experimentation, it's not obvious why it should be true, is to replace each of those phi of yks with some phi of something that's linear in x and linear in k over square root s. So I have some coefficients here. Doesn't really matter what they are. And then I have some function here of k. And as long as I replace this by this, the errors don't accumulate too much, and I get a good estimate for f of x, which looks like this. Now what we would like to do is say, we understand this thing as well as a little phi. Right? I can replace those pk's with a little phi of something. But it turns out that this error is too much, accumulates too quickly when you do that. So we have to use summation by parts and this global rule instead of the local one. And if you do that all very, very carefully, with lots and lots of mistakes and do-overs, then eventually you can estimate it like this. This is coming from doing that summation by parts, switching around. And now we'll view this thing like we would see it through the mean value theorem and replace it with, instead of capital phi, with capital Phi's derivative, little phi. And now this thing looks like a Riemann sum for a nice, pretty integral. So lots and lots of steps of integral. We went from that very discrete looking thing, and at each step keeping the error under control, down to this integral. And so at this step you could use just some calculus and eventually compute this out to be capital Phi of x. But if you look in the paper, there's a cute probabilistic proof of this instead. And that gets us to the end of the proof of the main theorem. And I don't have time to tell you the other pretty stuff I wanted to tell you about, but I'm at least got through all the tools and the proof.
Oh, you have 7 minutes.
I have 7? Is my watch fast? Oh, great. Okay, then I will talk a little more. Or are there any questions at this point about the proof?
Yes.
Yes.
So my only question is it any possible to computerize some of these beautiful human steps? And like all this manipulation of summation by parts, is it possible to one day have a computer do it for you?
I don't know. So the computer was actually really helpful in doing these steps because, like, when we needed to go from here to here, we weren't really sure what to do, and I used the computer to check if like statements like this were true, and we experimentally figured out what these coefficients should be, and then proved it after we knew what the answer was.
Yeah, so
it wasn't automatically do it, but it was definitely a helper.
Okay. So it's not complicated to the center.
Yeah.
Yeah, you have 6 more minutes.
All right, great. Okay, so that's, at least to me, satisfactory explanation of what Zaleski gave evidence for, why we're getting a normal distribution. Because we're really mixing normal things together with normal weights. And somehow that works. Somehow mixing normals with normal weights gives you a normal, if you do it right. But I just want to give some kind of musical ideas for why you don't get something normal without the distinct parts restriction. So for that, we need to look at Anderson's bijection. I've been teasing the whole talk. So Anderson didn't just show that there were finitely many ST cores. She actually gave a nice bijection to something that's obviously finite, which are ST dick paths. So, for example, examples are the best way to show everything. If we were looking at 5-7 cores, the way to generate all of them without making any mistakes is to look at the 5-7 grid. And draw a line from corner to corner. And we're going to look at paths which stay above that line. So there's other color over here. Here's a good path. Stays above that line. And I'm going to just shade in the cells that are cut through by this line so we can see clearly what we need to stay above. I didn't really draw it correctly. Okay, so these shaded cells, we're going to take all the paths that stay above them. And this is going to correspond to some 5-7 core in the following way. I'm going to put numbers in each of these boxes by putting an imaginary box here with the number 0 in it and saying that when you go up, you're going to add 7. And when you go right, you're going to subtract 5. So if I add 7 and subtract 5, I get 2, 9, 4, etc. End up with these numbers. And now I look at at which numbers are underneath my path and which numbers are above my path. And I write them in a column here from smallest to biggest. So I have 2, 3, 4, and 9. And now I just extend the rows so that these are the hook lengths in the first column of some partition. The only way to do that is like this. And if you put the hook lengths into the other boxes, you will be surprised to see that there are no 5s and no 7s. So it's kind of magical why this works. But we're just going to use it as a black box. We're just going to trust Anderson that she knows what she's talking about, and this gives us a bijection. So it's clear now that there are finitely many of these things, because there's only so many paths that you can do here. And what is special about this thing that Zaleski was talking about, that you look at SS plus 1 and then you look at distinct parts? Well, when I do the same thing there, when I draw this SS plus 1 grid and put the numbers in the boxes, it's going to have a very specific pattern. So you're going to have your diagonal, and then above it you're going to see 1, 2, 3, all the way up to S minus 1. And above the 1, you'll have some numbers and so on. But under this bijection, when do I get two parts of equal length? I get two parts of equal length if I have consecutive hook numbers, right? That 3 and that 4 both give me a part of size 2. So that's what we want to avoid. If I take the 1, I don't want to take the 2, and vice versa. So in particular, I better not put this cell underneath my path, because the dict path condition would force me to have both the 1 and the 2. And to avoid having both the 2 and the 3, I better not have this cell under my path either, and so on. So you're forced to stay in this first diagonal of numbers. And what that's really doing is getting rid of a lot of dependence. So if I imagine that each cell has a 0, 1 random variable, and it just tells me whether or not that cell is under the path or not, then here, 1's random variable and 2's random variable are definitely not independent, right? But 1 and S plus 1 are practically independent. If I know that this is under the path, I have basically no idea whether S plus 1 is above or below the path. They're almost independent to each other.
And therefore, to have a heuristic proof.
Exactly, a totally heuristic proof. That what we have here are S plus 1 sort of independent random variables. So there should be a sort of a central limit theorem. But that's not what's happening in the general case. There's a lot of dependence up here. If I take this 16 under my path, then I am forced to take the 9 and the 2 and the 4 and the 11 and the 6 and the 1. The further away you go from the diagonal, the more weird dependencies you get, so the less you would expect something normal to happen. And this heuristic proof works for two other cases that I didn't mention yet. So there's two other results in this area by the same people. So first, in the case... Oh, okay, so whatever. It works in the other cases too.
Okay, thank you very much. You can tell me talk, I understand why this is normal and why this is not.
It's illegal to make remarks after 48 minutes, right?
Yeah.
Okay.
Yeah, Emily, Dr. Sergel will be glad to answer questions in private.
Yes.
And if you'd like to join us for dinner,